Welcome to the Futurati podcast. Any member of the Futurati is somebody who believes in the power of the future. We know there's a better world ahead, and we indeed have the power to make it so. In our podcast, we talk to the best minds in the world about the most urgent problems facing mankind today, and we hope you learn as much from them as we do. I'm Thomas Fry, a professional futurist and keynote speaker.
And I'm Trent Fowler, a machine learning engineer and author. Thank you for joining us. All right, everybody. Thank you for joining us on the Futurati podcast. Today, we're interviewing Michał Stęchły, who is a Polish software engineer now working with Zapata on their quantum computing platform. Michał, thanks for being with us today.
My pleasure. Thanks for having me.
So for the most part, your work consists of building software tools that let other people access quantum hardware. Tell us about what that process is like.
So a lot of this process is similar to building classical software in the sense that there is a lot of things that need to, be in place to run quantum computer. So since most quantum computers nowadays are accessible via cloud, you have to, connect to this device. You have to figure out how the API works. You have to run, compile the circuits and so on. So a lot of that process is just like regular software engineering. But there are a couple of pieces that are, I would say, distinct or specific for quantum computing. And one of these is the fact that I'm not even saying, about writing algorithms specifically, just about tools for others to access. So one of the issues that we have in quantum computing is that it's such a new field that oftentimes the libraries change very fast. So, all the software packages that other vendors are producing are changing. So you have to adapt very fast to that. And it requires continuous maintenance and continuous work to keep everything up to date. So that's definitely one thing. The other thing is that we don't have, as a field, worked out all the useful abstractions yet. So if you are working on quantum circuits, you usually work at very low level. And one thing is that we don't have good enough abstractions. Another thing is that simply the hardware is so, so crude nowadays that you need to have control over, you cannot afford to make mistakes even on the lowest level. So
does that mean when you're programming, the computer has to be 400 degrees below zero, and then you have to wear parkas and everything when you're typing? Is that what you're doing?
Well, fortunately not. No. Fortunately not. But what I mean is that when you are writing software for classical computers, you don't need to think about NAND gates, right, or AND OR gates and compilation. In quantum computing, the problem is that every single gate in your quantum circuit counts, and every single gate adds additional error to the overall process. So you need to have that in mind. You cannot go too high in the layers of abstractions, because you will simply lose control over all those details that really count.
Okay, so I have several questions about the abstractions layer and how that impacts the usability of the quantum computers that you and other people are working on. So how high up the abstraction stack would you say you've gotten? So obviously when I write computer software, I'm not thinking about any of those things. I mean, I'm thinking of, for loops and while loops and recursion and things like that. Presumably when programming quantum computers, you are hovering significantly closer to the hardware. So I wonder if you could talk a little bit about how much you've been able to abstract that out. And then I'm curious as to how that's impacted the sorts of people that are able to use quantum computers and what they're able to build with them.
Sure. So, well, not surprisingly, it all depends on what exactly are you working on. Because usually at the beginning, when you are working on some algorithm, you work on a simulator, right? And simulator, well, it's more forgiving than the real thing, and it's ideal simulator. And you basically can run it on your own laptop, so you don't care about the costs. So you can work a little bit higher on the abstraction level. So what usually you have is, for example, for the thing I'm mostly focusing on, which are variational quantum algorithms, like a class of algorithms for quantum computing. There are some building blocks so that I usually don't think about which gate goes exactly where in my circuit. But then when you start thinking about making this code more efficient, about compiling in on a specific architecture, so like different chips have a very different architecture, then you start to think, well, okay, I have 5 different gates that basically can do the job that I need. So which one I need to choose, right? To actually be able to run it on the real hardware, or the hardware has like this specific layout, which means that like certain qubits are connected to certain other qubits. So we start thinking, okay, can I actually encode my problem a little bit differently so it fits the layout better, right? Maybe some parts of the circuit that I have are not that important. Maybe I can, omit them or like move them elsewhere, so that I don't need to perform operations that are very costly on this specific architecture. And then you're getting lower and lower on this stack. And something that I personally never done, but I know some people who are working on this level. They're working on the level of the pools, right? So each gate in a quantum computer, depending on the specific hardware, but usually it's like some kind of the microwave pulse. And the way you like shape this pulse changes the behavior of the gate. So it turns out that you can tune the shape of the pulse to actually get more precise gates. And well, this is the level of abstractions you can get on. It's like having I guess it's like similar to having a classical transistor and like tuning the transistor to behave in a certain way to perform the NAND or operation where like the specific voltages levels are crossed or not. And people are doing this like nowadays, like they are on this level, and that's not something uncommon, I would say.
Right. So that it doesn't sound like an abstraction at all. I mean, you're down there fiddling around with voltages and microwave pulses. I mean, that's just physics. You're dictating to physics how it's supposed to operate in order to execute these logical computations.
Yes, but for example, I never did that, right? I operate like higher on the abstraction layer, so I usually work on those higher level building blocks of kind of variational algorithms. So instead of working on specific gates and like putting those gates in the circuit one by one, I more often like use layers of gates. So I know that like now I apply X gate on every qubit, and then I apply like C naught gates on like every pair of qubits, and then something else happens. So it's still pretty low level, but at least a little bit like much higher, I guess, than the microwave pulses.
At the level of a gate, yeah. So
Yeah. I wanted to ask you a little bit about the stage that we're in on quantum computing, because I mean, people have been working on this for quite a while, but it would seem like an analogy here is that we're still at the kind of the mainframe computing level, and maybe 20 years from now we get to the personal quantum computers, and then we start over with the homebrew clubs and stuff like that. People have their own quantum computers in their basements, and is that a possibility? Or
So there are I would say, like, to what you said, like, there are two fundamental reasons why it probably won't happen, and why our perspective and comparisons with the kind of classical computing may be a little bit off. So the first reason is the personal quantum computers might not happen because, well, first, for most quantum computing architectures, we will probably not be able to escape this like almost 0 Kelvin cooling equipment. And I don't think you want to have this kind of refrigerators in your basement.
Okay.
And that's like one thing, but the other thing that quantum computings are much less universal in what they can do than classical computers. I mean, there are people writing games using quantum computers and things like this, but for like a kind of regular person, they might not have enough appeal because, you know, not everyone is interested in solving optimization problems, in solving quantum chemistry problems and so on. And I think like people were able to do like kind of much more mundane things with regular computers in the early days, though I wasn't there, so I might be off here. And the second reason is that actually we have classical computers to help us build quantum computers. And this is something that also might like skew the timelines and, you know, make this progress faster because, well, we have very, very powerful tool at our hands right now. Though maybe the engineering and scientific challenges are even bigger than they were. So it's like, you know, hard to say.
Yeah, well, I'll make the analogy that we're actually getting to a point where we have backyard nuclear power plants as well. So that's something we never thought we would want to have in our backyard either. So
yeah, that's true. But I don't have one in my backyard. So, you know, hard
yeah.
to say.
Yeah.
Something else that I've been kind of wondering about with respect to the proliferation of quantum computers and the possibility of a personal quantum computer is the way the economics is different this time around. So I think there are at least two major respects in which this is the case. The first is that we have cloud computing these days. And so it's not necessary for you to have a quantum computer in your basement, notwithstanding the temperature problems, because you can just have an API call out to AWS Bracket, or I think Zapata's is called Oracle. Is that right?
Orchestra.
Okay.
Yeah.
Orchestra. And then also you've got economic competition from the saturation of classical personal computers, which are everywhere now. And so a personal quantum computer would need to be much, much better for the specific applications that you are wanting to interact with for it to be worth developing a personal quantum computer. So I don't know that the market is there, and I was wondering if you'd comment on that.
So I don't think there is, but it doesn't really mean anything, in the sense that it was probably really hard for people, you know, developing computers in the, like, I don't know, like 50s, 60s to imagine like how you can use these machines for kind of personal use. And there are some people that probably could imagine these things that we are doing with computers now, but most of them probably had a hard time doing that. And I think the same applies to quantum computers. That, like, I don't see what like a person who is not, you know, kind of super interested in like science would do with such device. But this doesn't mean that someone wouldn't find this out in like a couple of years. So as I said, like, for example, some people are playing with quantum computers to make computer games. So there are like, I've heard about one guy who use quantum computer to generate randomly levels on like some game map or something like this. So it's pretty cool stuff to do. So if some people might be interested in that, that's for sure. But yeah, I don't think it will happen, at least in the next 10 years. Probably the cost would be, too high, and the access might be a little bit scarce.
Okay, so you've said that when you've had the chance to do research, you tend to focus on what are called variational quantum algorithms, and you've described these as being hybrid classical quantum algorithms. So let's start with you just saying a few words about what that means. So how is it that an algorithm can be hybrid classical quantum? Are parts of it quantum and parts of it classical, or do they interface in some way?
Sure. So there are many different ways that this can happen. And to be honest, I think most of the quantum algorithms are in some way hybrid, at least for the sake of the fact that you have to put some kind of data on the quantum computer, and you don't do that kind of by hand and by like manual switching, some like pushing some buttons on the computer. You do that using software. But in this case, the hybrid element is that in variational quantum algorithms, we use quantum computers to compute some quantum state. And this quantum state usually has some information about the, for example, quantum system we want to simulate. So for example, out of this, we want to find the minimum energy of like some configuration of a molecule. And in such case, we kind of try to simulate this molecule on a quantum chip. And when we read out from the quantum chip what's the state of it, what's the quantum state, we can calculate energy out of that. And this is the part that quantum computer is doing. And the reason why we are doing it on quantum computer is that simulating molecules is very hard on a classical one, but much like easier on a quantum computer. So this is the only thing that we are doing on a quantum computer. Then when we actually got the energy from the quantum computer, or like the cost function value that we wanted, then we use classical optimizers to modify the parameters of the quantum circuit. So we basically say, okay, let's change this parameter in this gate, that parameter on the other gate, and let's try again to produce even better approximation of the state of the molecule that we wanted. So basically, we have an optimization loop where we use quantum computer to calculate the cost function, but all the other parts are classical.
So that's really interesting to me. It's not intuitively obvious that a classical optimizer would be able to handle the hyperparameters on a quantum circuit. So is that a result that's well known? Is that the way people tend to do it? It's just not clear to me that, like, I wouldn't have guessed that was true.
So I like to think about quantum computer in this scenario as a black box. So you basically can have a black box with some parameters, and you don't really care whether it's a quantum computer, regular computer, or like a person sitting with a notebook and handing you out like kind of cards with numbers. You just give some parameters in, and you get some other result out. And you can use kind of classical optimizer in any of these scenarios. I would say that the performance of the classical optimizer might depend on the nature of this black box, right? So it might turn out that some optimizers work better or worse with certain types of black boxes. So this might be like non-intuitive, but fortunately, classical optimizers work pretty well with this quantum, like quantum circuits.
Are there quantum optimizers?
Not really. So usually, for those who know these terms, like we use optimizers like BFGS or Nelder-Mead, Kobaila, SPSA, Atom. There are some optimizers that are kind of more prevalent in the quantum world, I guess, because they turn out that they work slightly better with quantum computers. So one of the characteristics here that you want to take into account is the fact that your optimizer, like every evaluation of the cost function is expensive. So you cannot use optimizer with just runs, millions and millions and millions of samples to make it work. Even because on the classical computer, this might be cheap and fast. On the quantum, it's not. So you rather want to choose optimizers which need like less cost function evaluations. And also there are like some specific things about the kind of optimization landscape, energy landscape of the problem you're trying to solve that also make some optimizer work better or worse. So I wouldn't say there's like a quantum optimizer, at least not yet. Some people, like you could propose in principle to have a quantum computer running an optimization algorithm to optimize parameters of the other quantum computer, but we are definitely not there yet.
So is this one of those things where people just sort of messed around until they found that Atom or one of these other optimizers tends to work pretty well for quantum computers? Or are there deeper mathematical reasons, sets of proofs that demonstrate that the features of this optimizer are such that it's better for a quantum computer? Because a lot of machine learning is just sort of firing into the dark, and when you hit something, you stick with it.
Yeah, so I would say more firing in the dark, but on the other hand, I'm not kind of very theoretical in my approach. So I might simply not be able to appreciate some of the like, deeper reasoning that went in. Though I never heard any like compelling reason for like fundamentally why, people say this should work better or worse than the other one. I wouldn't say if such research exists, I wouldn't say it's like very mainstream. Most of the time, it's more like experimentation, and people like developed. I remember like last year, Google proposed like a new optimizer in one of their papers for quantum computer, where they simply modified one of the gradient descent method to kind of account for the fact that every cost function evaluation is expensive, and you kind of don't want to do too many of them. But more experimentation, I guess.
So a little over a year ago, Google claimed they had achieved quantum supremacy, and they were kind of beat over the head by a lot of people saying, "Nah, you didn't really do that," even though they had solved the problem that was given to them, and so it was essentially solving a problem that would have taken traditional supercomputers 10,000 years to accomplish. And recently, a new headline came out that said that China has developed this ultra super quantum computer that did something that would take 2.5 billion years, and they did it in 200 seconds. And so I'm not sure how you quantify something that would take 2.5 billion years, but are we moving up this exponential curve way faster than people imagine?
I don't think we're moving way faster than people imagine. Though like the progress is definitely good. Regarding, I haven't like dig too deep in this like recent announcement. For Google, well, they designed this experiment in a way that it would be hard for a classical computing, and it would be relatively easy for a quantum one. So you can like they show that you can create a problem where quantum computer works better than classical today, and this is, from a scientific point, it is very like valid and important result. From the perspective of like practical application, not that much, I would say. But I mean it's important though. If the problem in quantum computing is that it's like very easy to like overhype something, and sometimes like probably even often like people unintentionally say something that they think is kind of obvious, that there are some caveats to it, but popular press journalists might not know that, so they kind of twist it a little bit, or just like omit some important part that they didn't know is important, and then suddenly you get some like headlines.
Yeah, that almost never happens.
Yeah, that's true. That's true.
Yeah, well, journalists are well known for their scientific credentials and their impeccable integrity.
Yeah.
But to keep with this, so you said that variational quantum algorithms could be key to developing useful quantum computers in the near future. So we know that theoretical results are quite important, but around here we're pretty interested in the near to medium term economic viability of quantum computers. So I was wondering if you could talk a little bit about the applications of quantum computing technology to various problems. And you can stick with variational quantum algorithms if you want to, or just speak in general about the new technologies that are emerging.
Yeah. So actually, like the last week, so it was like December 2020, there was Q2B conference, which is one of the, or even the biggest kind of conference about quantum computing and business. And one of the, in one of the lectures, one of the presentations, some researchers said that they surveyed the field, and it looks like there are three main fields where quantum computing would be useful, and like interests is distributed pretty evenly among the three of them. So this is quantum computing for simulations in chemistry and materials. The other is optimization, and the third one is quantum machine learning. So these are like the near-term, things that people focus on. And I would say that for quantum, there's a lot of research going on in different directions. It's really hard to say what would be, like the first that brings any viability. But there are probably some distinct features of the problems that would actually bring value to the market in the near term.
So
yeah.
one of the ways we look at this is in terms of the killer app, the app that everybody has to download on their computer. So is there such a thing as a killer app out there for quantum computing?
It doesn't seem so yet. It seems that there is a lot of gradual progress that we'll be doing, and just like improving the results step by step. But it doesn't seem like there will be one thing that will like revolutionize everything. At least in the short term. In the long term, I imagine, well, one thing, Shor's algorithm and breaking RSA looks like it might be a nominal killer app. But the other things definitely might be from the chemistry simulation optimization. There are some reservations in the community about the optimization, because the type of speed up that we can prove we can get from quantum computing are only quadratic, so like n squared, and not exponential as in case of chemistry. But to be honest, this is like still open debate, like how useful the quantum computing would be in the end, because as in machine learning, a lot of methods are heuristic and we don't have kind of proofs of the speed up. It turns out that neural networks are pretty good for a lot of tasks. And it might turn that with variational quantum algorithms, they also don't have this like guaranteed speed up, but it might turn out that they actually allow you to solve a lot of problems much faster than classical ones, even without provable speed ups. So I would say that in the next 5-10 years, I would rather expect quantum computing to give like maybe 5 years. Not sure about 10 years. A lot can happen. But in 5 years, more like gradual speed ups to very specific problems that would require a lot of effort to just like map the problem from the classical space into the quantum space. And once we prove that this is possible, then it can kind of propagate and grow. An example I particularly like, and this is something I heard from my friends who are quantum chemists. I don't know the nitty-gritty of this process, but basically the VQE, so one of the kind of most important variational algorithms, we can use it to estimate the ground state energy of a molecule. And while ground state energy of the molecule by itself is not like extremely important, I mean, knowing like this single value won't allow you to build anything like revolutionary. It actually is one of the first thing you kind of put into the huge computational pipeline when you are making simulations for materials, molecules, and so on. So just if we can, have this initial value, get it more accurate by like 10%, it will make all the like other values in the chain more accurate, right? Or maybe they will start converging faster because they're closer to accurate and so on. So it will probably bring some improvements to like whole computational pipeline in like chemistry simulations, material simulations, and this might be very valuable, but not groundbreaking by itself.
So I think it's fair to say that doing quantum chemistry simulations is probably not going to be the killer app for quantum computing. I don't know that the average person cares enough about the ground state of molecules to be messing with it. But we interviewed Mark Jackson, and he said that the day could come where Google Maps has an API call out to a quantum computer and is using that to do some sort of traffic route optimization. And you might be using quantum computers and not even know it. So I'm curious as to whether or not you have any sense of the kinds of problems for which a quantum computer is uniquely suited to solve. So, I mean, obviously simulating a quantum mechanical system is sort of a gimme, but outside of that, predicting the weather or optimizing, portfolio parameters, do these things share any common features?
So I would say that problems. Okay, so actually, there is one application that seems unreasonably promising to me, which is natural language processing.
Right.
So again, like this is from one of the talks that from the recent conference, but it seems that the language has some properties, if you express it as like kind of mathematical model, that resemble the quantum systems. And actually, quantum computers might be pretty good at like processing natural language for the reasons I don't fully comprehend. But this is like, I would say, very surprising that the first time I heard about it, I thought, well, this sounds just like, like buzzwords to me. But it turns out that there's like some deeper rationality why this might be true. Apart from that, usually the problems that quantum computers would be particularly suited are the problems that have like small representation, but very rich space of states, in the sense that combinatorial optimization problems are, this kind of problems, right? Because even though you can express solution to a problem in like several bits, right, of several numbers, actually the number of configurations is really huge. And so this problem is with like kind of narrow, at the beginning and the end, but like very wide in between. These are problems that probably will suit quantum computers well.
Yeah. I often do a lot of work on the autonomous transportation space, and the idea of actually managing a whole traffic system with millions of cars around an entire country or multiple countries, and then making sure that the right cars are in the right place at the right time, figuring that we're going to have people who want the cheap vehicles and people that want the more expensive vehicles, and there's probably going to be like eight different grades in between, and then making sure that they're maintained properly, and they're checking all the sensors in the vehicles as people are coming and going, and understanding all of the things that can possibly go wrong. It seems like there are truly a staggering number of variables involved in autonomous transportation. Is that something that would lend itself better to a quantum world or traditional computing?
So it probably won't land very well to quantum world, at least not in the foreseeable future, because there are so many variables. And if we have a quantum computer with like million qubits, which is a lot, then if you even use like every qubit to kind of encode one bit of information, it's like like not that much information that you can encode, right? And people are working on ways to kind of get around this and actually push more data into quantum computers in different ways. But this doesn't seem like a kind of good fit for quantum computer. But on the other hand, what seems like a better idea are more like high level problems, for example, of design, or like designing the whole system, in the sense that it might turn out that the problems where you solve something once and even a small increase in the quality of your solution leads to very a lot of value, is a better, right? So instead of solving traveling salesman problem, every day, every time you kind of make an API call to the Google Maps, at least for me, it looks that a better solution would be to have using quantum computer for, designing the layout of the city better, right? Or something like this. Because this is something that you can spend weeks running the computer nonstop to compute it. And if you get a solution which is 3% better than the best classical one, it's actually, you benefit a lot.
Okay. Yeah. So it sounds like the big bottleneck there is just not having enough corrective qubits to do the calculations you want to do, right? And that's sort of a big problem, the difference between physical and logical qubits, and it's pretty difficult to get enough logical qubits to do computations that are really sophisticated. Do I have that right?
Yes. Yeah. I mean, there are plenty of problems, but that's definitely one of them.
So you have this effort, it's Q for Climate, is that right? Trying to use quantum computers to solve climate change. So it seems like that would require a lot of qubits as well. So why does it make sense to try to use a quantum computer to solve a problem like climate change, which, I think we can agree has quite a few variables, as opposed to something like building a better classical supercomputer?
So a Q for Climate is like the initiative that, with a couple of other people from quantum computing community, we are putting together. And our aim is to just, do research and find places where quantum computing could actually help. So identify what are the kind of most useful cases where quantum computing could help solving climate change in one way or another. So when we are doing research, it turns out that actually, some of the ideas that one might initially have are not a good fit for quantum computers, right? Because, so on one hand, modeling kind of the whole model of the Earth climate, this doesn't look like, very good fit for quantum computers, because there are just so many variables, and you would need really a huge quantum computer. On the other hand, things like maybe optimizing the wind farm and where each wind turbine should go and how it should be adjusted. This might be because perhaps you can solve this optimization problem on a quantum computer and get better result done on the classical one. And I don't think by any means that quantum computing would be a silver bullet for solving climate change problems. But what we would like to see is like actually make the community use quantum computing for solving this particular challenge instead of many other challenges that we don't think are as pressing nowadays. So I would say that actually in a lot of cases, it makes much more sense to invest in classical computing for solving these challenges. But quantum computing is, I like think about it as this like enabling technology in some sense, that it's hard to say when it's more mature. It's hard to see for us today what it will allow us to do and like what kind of possibilities it will unlock. Because just being able to simulate like new materials or so maybe or like improve the accuracy of chemistry simulations. This might be like really a transformative thing, right? So two examples. One is there is this process in the nature called nitrogenase, which we use for creating the fertilizers. And we know that in nature this process can occur at kind of regular temperature, regular pressure, but on the industrial scale we're doing that. We don't know how to do that in this conditions. So we use a lot of very high temperature, very high pressure, and it's actually a portion of like Earth's like energy output to just like kind of produce fertilizers. And it seems that simulating one of the molecules that will help us understand how this process works in nature, it might help a lot, and like it might allow us to like lower the energy consumption. So this would be like a big deal. On the other hand, it's debatable like how big quantum computer you would need to actually solve this problem.
Yeah, so I think that people tend to underestimate the impact of incremental changes. It's easy to lose sight of what it would mean for chemistry simulations to be 15 or 20% better, or to optimize the production of fertilizer such that it takes 20 or 30% less energy. Like what that would mean in terms of freed up calories, and in terms of better production, in terms of like better yields all across the earth. I was wondering if you could lay out some of the other areas that your research group has identified as being good candidates for use with quantum computers. So wind farm layout optimization, that's really cool. I never thought, I mean, my mind immediately just jumped to weather simulations, right? That's just sort of the obvious thing. But what are some others that you've identified?
So I wouldn't say any of this is like definite. We try to be very careful about making any claims, and we want to do very, very like proper research first, and then kind of throw around ideas. I would say some other potential like directions that look promising could be using quantum computers for solving differential equations. So that's like not my specialty, but there are some quantum algorithms for solving differential equations, and differential equations are like in a lot of places. So if these algorithms are more for the kind of long-term quantum computing, but if we are able to just like again, like concrete example would be like design the wings of the airplane better, right? And just reduce the consumption of the airplane by like 10 or 20%. That would be great. I don't claim using quantum computer would kind of lead to that output, but perhaps it could, right? So this kind of use cases, like I would say differential equations might be promising, but they require a lot of more research. From optimization problems, wind farm optimization, maybe there are some problems in like network optimization, like electricity network, electricity grid, especially once we shift to more like this new paradigm of energy power systems where you have like a lot of producers and not like a couple of centralized ones and so on. There might be optimization problems that might yield to quantum computers, but there might be not. Like as I said, like it's really hard to say. And in chemistry and materials, yeah, like as well, like this nitrogenase is one of the like one example, but there are a lot of like chemical reactions that are happening on an industrial scale that could be done more efficiently. Though, as like none of these looks like a killer app, to be honest. Maybe this nitrogenase, but still they're like it might be not that easy to actually do that. But I don't think right now there's like any single killer app that like quantum computer would like significantly help solving climate change in the next like 5-10 years. Maybe in 20, but that's like too far away in the future to really say.
Yeah, one of the discussion points we'd gotten into in the past was about actually doing purchase transactions with cryptocurrencies, and how the blocks in the blockchain have gotten too big and too massive to make that convenient because it takes too long a time to process them. You go to a Walmart store or someplace, and it becomes painful. Is that something that could be somehow streamlined with the quantum engine in the background?
So I don't know. I've never heard about. I mean, from time to time, people ask about this like quantum and blockchain kind of use cases, but I've never heard about any like significant work in this field, in this like cross section. From what I heard, it seems that it's unlikely, but who knows?
We can just keep putting buzzwords together. Like, how about an AI on a quantum blockchain? Does that get your motor turning? Okay,
it does.
So I wanted to ask you. So, like me, you take the ethics of technology very seriously, and in the material you sent over for us to prepare for the interview, you noted that you're interested in effective altruism. So I wanted to ask a couple of questions about that. And the first is, what's your framework for evaluating the benefit or harm of a technology? So it's obviously very difficult to forecast how people will end up using it, but how do you sort of get purchase on that question and think through the ramifications of a new technology?
So, well, I wouldn't claim I have like very rigid framework. And, whenever I see, interesting in technology, let's run it through a checklist and see, how promising or harmful it can be. But this is something I try like kind of think a lot about and try to learn. But I would say that one thing are potential benefits, definitely. So, like if this technology go like really well, right, can it benefit humanity in some tremendous way or in some moderate way, right? So I don't know, like quantum computing has like a lot of like kind of potential, right? We don't know how much of that is true, but ideally, like the potential is like really huge. While I don't know, producing more efficient pencil sharpeners, well, it has like kind of limited cap on like how beneficial it could be, right? And on the other hand, the same about harm. So how harmful it can be. So like some biotechnologies, right? They can be very beneficial, but potentially they can also be extremely harmful. And this is something to kind of keep in mind. So one of the things is that I like keep asking myself, like, how this technology can backfire, right? What if all the things that can go wrong? Can it like basically be an existential risk? So can it produce a risk that like the humanity will either die or like lock in some like very kind of dystopian way, or there are like a couple of scenarios that things can go wrong. So that's one thing. The other thing is more about like, I would say, second order effects, that even if this technology maybe directly doesn't cause harm, maybe it can accelerate some processes that are not beneficial for humanity. So, for example, the one way that quantum computing can indirectly cause harm is that it can lead to further like faster advances in AI, which in turn can lead to developing some like rogue AI that can be harmful for humanity, or it can lead to much easier like lowering the costs of some biotechnology procedures, which in turn might, for example, lead to producing like some new bioweapons or things like this. So while in case of quantum computing, right, like directly it doesn't look like increasing computational power is very harmful, it might indirectly affect us and cause some harm. So yeah, that's like two things that I usually think about.
Right. So one of the second order effects is how it would enable bad actors to take control of resources, or to oppress people in various ways, or to protect themselves while attacking other people. How do you think that we should go about developing quantum computing such that it's more likely it's used for good as opposed to evil?
So one thing is definitely have some very smart people to think about this problem, and just like have, I would say, experts in technology ethics, technology development, like look into this, and the earlier people look into this, the better. And I know about like some initiatives in regarding quantum computing ethics, but I don't know about kind of any external for quantum world people investigating that. But this just might be my kind of limited perception. But this is one thing. The other thing is having people in the field, think about it and feel responsible for like this kind of issues. Because I might be a little bit naive, but I think that if you have a company and in this company wants to use quantum computing for like making money at the expense of some group or someone, then if like all the scientists in this company say, hey, we are not interested in like developing this and we will quit if you keep working on this project, then it puts pressure on the on the company, right? So if we have people in this field who have this kind of like, I don't know, like civic courage is the right kind of word, to like stand up and say, this is a bad use of this amazing technology. The more we have that, the kind of more resistant we are to using it for the bad. Though, well, that will be in the kind of ideal world, I guess. I know like the real world is much more messy. But definitely just like talking about it and like having discussion around it is like the first step. And I'm happy to see like discussions like this in the community. Also, the more So one of the cases where this comes up often is the cybersecurity, right? So if we develop quantum computers which are able to break RSA, then this might lead to some kind of very dangerous situations regarding like privacy, like stealing data information from one another and so on. And the problem is that if we don't start to think about it right now, we'll not develop the protocols, like cryptographic protocols, that are resistant to quantum computing. And there are such protocols, and like people are working on that. But they need to be in place, before the quantum computers are powerful enough to break the protocols that we have today. Furthermore, for many actors, like governments, banks, and so on, they also care about the data that like the past data, right? So some bad actors might be already starting gathering the data from today, which are encrypted, hoping that in 20 years they will have quantum computer powerful enough to decrypt that data from 20 years. And some information is garbage after 20 years, but some other information might be still very valuable. And similarly with other cases, well, it's just like worthwhile to think about it right now instead of waiting until the technology matures, because this is a case which we can imagine today. So the more people think about it, and the more people try to figure out how the technology can backfire, that like better prepared we can be for future.
Absolutely. So I wanted to wrap up on a slightly more a happier note. And I know that you spend a lot of time on mentorship and community building through efforts like the Quantum Open Source Foundation. So I wanted to just give you a couple of minutes to advertise for that and talk about what that looks like, who's involved, the kinds of projects you work on, anything you want to discuss.
Sure. So Quantum Open Source Foundation is, our goal is to support the development of open source software in quantum computing, to popularize and educate quantum computing, like foster the community. Which, coming back to the previous question, we also believe it's like good for everyone, because the more open the field is, kind of probably the better it is for like the free flow of the knowledge and so on. But we have, as Quantum Open Source Foundation, we have a couple of initiatives that we do to like achieve that goal. So one that I'm mostly involved in is the mentorship program. So the mentorship program is the program where we have mentors who are professionals in the field or academics who are working with their mentees who are like interested in quantum computing, want to, they're like often they're students, software engineers who want to kind of learn more about the field. And they work for 3 months on some quantum computing project in an open source manner. So the benefit is like it benefits everyone, right? So, community gets some cool projects, some contributions to existing projects. The mentees, really learn a lot in the process, and mentors also, are happy to kind of give back what they know, and they also learn a lot when they teach other people. So this is the project I'm like overseeing and like I'm working on mostly at QOSF. Right now, there's the second batch, and during the second batch, we have about 20-something mentors and about 30 participants who we selected from total of 750 applicants. And the batches are roughly like the projects are 3 months long. So the current batch will finish in January, and in January we'll also open recruitment for the next the applications like for the next batch. So the next batch applications will be open like end of January, early February. In the March, we want to start the third batch and like just introduce more people into the community and do some more cool projects. So that's what's happening at QOSF. If anyone is interested, go to www.qosf.org and there's like a webpage about mentorship as well.
So if somebody wants to get in touch with you, how do they do that?
So I have a blog which is called Musty Thoughts, and you can find like all the information about me. You can learn more about quantum computing. There is my email there. So I would recommend to just go there and find me, or Twitter, LinkedIn. That's also always a good option.
All right.
Well, fantastic. Thanks so much, Michał.
Thank you for having me. Have a nice
Thanks.
afternoon.